Hello, and welcome to Astronomy 100. In this video, we're going to continue our discussion of Newton's laws. And remember, our ultimate goal is to understand the concept of orbiting bodies. Now, in the previous video, we defined a couple of terms that are necessary before we can understand Newton's second law. And really, the word that we were after there was the word acceleration. And to just remind you, remember that acceleration means to change your velocity over a period of time. So anytime something changes its speed or its direction, or both, over a period of time, it is accelerating. So let's get into this and we'll see what it has to do with Newton's second law. Now, Newton's second law, let's start off with the language of it. His second law says that the acceleration of an object is directly proportional to the applied force and inversely proportional to its mass. In words, he's actually describing a formula. And this is why in our previous video it was important to at least have the audience, have you students, understand the idea of what it means to have a direct proportionality versus an inverse proportionality. So what he says is the acceleration of any body, this is going to be signified by the letter A, is directly proportional to the applied force. So A is directly proportional to F, and inversely proportional to its mass. So A is inversely proportional to the mass. Remember, anything on the bottom is inversely proportional to A, anything on the top is directly proportional to A. Now, in this form of this equation, it gets the idea across, but in physics, it's very, very common to use a little bit of algebra to rearrange this formula. In other words, rather than solving for the letter A, what we're going to do is rearrange the formula to solve for the letter F. And when we do that, we get F equals m times A. Now, this is one of the most important formulas in all of physics. In fact, you spend a great deal of the first semester of a physics class exploring all the applications that go with this formula. It even has a name. It's called the first fundamental law of physics. Now, what it says in words is the force of an object is equal to the mass of that object multiplied by its acceleration. So let me actually do a slight variation of that to help you better understand what this means. What this formula is actually saying is that anytime a mass, and remember mass is a quantity of material, you have mass, your car has mass, a bullet has mass, whatever. Anytime a mass experiences an acceleration, the result is a force. So I'll say it again one more time. Anytime a mass experiences an acceleration, the result is a force. So let me give you a few verbal examples. If you were driving down the freeway, and obviously you and your car have mass, if you're driving down the freeway with your cruise control going, so the car is maintaining, let's say, 60 miles per hour, and if it's maintaining 60 miles per hour and you're not changing your direction, you're just going down a long straightaway, then your acceleration is zero. The reason why your acceleration is zero is because, remember, acceleration is changing your velocity over a period of time. If your speed isn't changing and your direction isn't changing by being in cruise control on a straightaway, then you have no acceleration. And so in your car, the forces feel like they're gone. It feels like when you're in cruise control going down the freeway, like you're sitting in a chair in your living room. And this is unfortunately why people tend to do things in their car they shouldn't, like mess around with their cell phones, texting. Sometimes I've even seen people read a newspaper while they're cruising down the freeway. But notice that anytime there is an acceleration, if A has any value to it, then F suddenly becomes important. For instance, let's say that you're on the freeway in cruise control and somebody in front of you decides to cut into your lane. Well, all of a sudden, by dramatically turning the steering wheel to get out and avoid the collision, turning the steering wheel is changing your direction. Even though cruise control is still going, you're changing your direction which is a change in velocity, which is an acceleration. The very dramatic turning of your steering wheel makes a very, very large acceleration. And so suddenly you feel the forces involved. It does not feel like you're just comfortably in your living room anymore. You have all sorts of things flying around your car. Your coffee might be spilling out of the cup. Simply by making a dramatic change, you are then, of course, changing the direction, changing the velocity, which is an acceleration, which is a force. So all Newton's trying to say is that in the world around us, we experience accelerations, and these accelerations that are involved in a mass that it's experiencing, the acceleration, are forces. This is why you have to have a seat belt, because if your car suddenly goes from 60 miles per hour to 0 in just 1 or 2 seconds, then of course that's a tremendous acceleration, which makes the forces acting on you feel like your body is going to fly through the windshield. So F equals ma is a big part of the world around us, and it has a lot to do with the things that you experience. Let me give you one more example. Let's go back to the 2 cars we talked about in the last video. My Chevy Vega from days of yore, long ago when I was young, and the Tesla Roadster. Now, each car has an engine, and each engine applies a force. And so what really makes a car experience a tremendous acceleration is really dependent on the power or the force of the engine, but it's also dependent on the mass of the car. This is why cars are made out of very lightweight materials. If you make a car very lightweight by using aluminum instead of steel or carbon instead of aluminum, carbon fiber has a very low mass, and remember, if I make M small, then the A becomes large. So a fairly small engine with a very lightweight car can still experience a very, very powerful or seemingly high acceleration. So that's why racing cars on the tracks, the Indy 500, etc., stock car racing, whatever, they are very powerful engines, but the bodies on those cars are incredibly lightweight or low mass because they want tremendous acceleration for the power that the engine provides. So it's just very much a part of the world around us. Newton's second law is around us in many, many different ways, shapes, and forms. Now let's move on to Newton's third law. Newton's third law is often quoted, but sometimes quoted and expressed incorrectly. So let's try to clarify that. Newton's third law says for every force, there is an equal but opposite force. So what it's really saying is you cannot have a force without a consequence. Every force has a consequence. Now let me give you a couple of examples that will, of course, maybe sound familiar. Let's start with this first one here. If you've ever, in the living room, let's say you're in a hurry and you race around your furniture and you accidentally kick a piece of furniture with your toe, obviously your toe hurts a lot, but what you don't realize is that's actually Newton's third law. The amount of force that you applied on the foot of the furniture by kicking it, the furniture applies an equal and opposite force on your toe. The harder you kick the furniture, the more your toe is going to hurt. And it's because your force has to be met with an equal and opposite force of the furniture acting on your toe. So that's Newton's third law. Let's look at another example. If you've ever seen a car accident where a car has hit a tree, the tree typically is broken and the car is also smashed. And the reason why is the amount of force that your car applies to hitting the tree will break the tree, but the amount of force that you applied, the tree has to apply an equal and opposite amount of force. So the force you apply on the tree applies back on the car. So you can't hit a tree and break the tree without also damaging your car. It has to be an equal but opposite reactionary force. So every force has a consequence. Here's one last example. In the early days of boxing, this is like an old-timey boxer here, notice the mustache, but in the early days of boxing, they did not use gloves. And of course, they quickly figured out that you have to use gloves. And the reason why is because the amount of force that the boxer exerts by punching the other boxer in the face that amount of force that the fist on his or her face would also be the same amount of force of their face on your fist. So when you bare knuckle hit something, it breaks your knuckles because of the equal but opposite force. So you cannot have the expectation of having people hit on each other without breaking their hands or their knuckles or anything that's involved. So obviously the gloves prevent that from happening. Now, there is a couple of applications that'll lead us to where we want to go. So let's bring up Newton's third law once again. Now I'm going to show you what's called a static example of Newton's third law. Now here is a laptop sitting on a table, and obviously from a previous video we talked about how the Earth is trying to pull everything towards its center. So the reason why things fall is because the Earth is simply trying to take the object to the center of the Earth, and we call that the weight of the object. So this laptop has a certain weight, and the weight of the laptop is the force between the Earth and the laptop, and the Earth trying to take the computer to the center of the Earth. That's a downward force. But clearly the laptop does not break the table and fall to the floor. And the reason why is because of Newton's third law. The table is providing an equal but opposite force on the laptop. Now how do we know it's equal but opposite? Well, it's equal and opposite because if the force upward was greater than the force downward, then the laptop would bounce off the table. If the force downward was greater than the force upward, then it would break the table and come all the way to the ground. So the fact that it sits quietly, sitting, doing nothing on the table, it is equal but opposite. And that's what the word static means. Static in this instance means not moving or stationary. Now let me show you a dynamic example. Anytime you shoot a gun, pistol, rifle, whatever, this is a dynamic force. The amount of force that the burning gunpowder in the expanding cloud of gas from that burning gunpowder is pushing on the bullet to make the bullet come out. So the force used to propel the bullet also has to exert an equal but opposite force on the gun because of Newton's third law. So every time you shoot a pistol or any other gun, you will always have recoil. So the recoil of a gun is the result of Newton's third law. The amount of force used to expel the bullet will also provide an equal but opposite force on the gun. Now let me show you how we can take advantage of this. So let's look at a cannon for a second. When a cannon is fired, it's very much like the pistol. The burning gunpowder, expanding cloud of gas pushes the cannonball out of the way. And so the cannonball gets pushed out of the cannon. And of course, as the cannonball goes out, the cannon often rolls backwards. So by rolling backwards, the cannon is showing you what we call recoil. Newton's third law, every force has to have an equal but opposite force. Now, what if we could make the cannonball go away? In other words, let's just burn the gunpowder and make the gunpowder come out of the cannon. But instead of a big wide opening to the barrel, let's pinch it so it's a small, narrow opening. Let's take the cannon, turn it so that it's pointed towards the ground, and if we just make the gunpowder burn and continuously put more gunpowder, letting it burn and burn and burn and burn, what will happen is the gunpowder and the gases will continuously come out of the cannon, but you will have continuous recoil as a result. And that's what a rocket is doing. This is very much just like the cannon. Here's the chamber where the gunpowder would burn. Normally the cannonball would come out like this, but we've simply turned it and removed the cannonball. And notice by continuously providing some fuel to continuously burn and the pushing out of the gases, as long as that continues to happen, then you'll have a continuous recoil. So the force of the gases coming out will force the rocket to continue to go in the opposite direction. So the upward thrust of the rocket is at the expense of the reactionary force of the gas coming out. This is Newton's third law. So it's really very much like a cannon, but it's just continually making the cannon go and go and go and go without ever stopping, and you have continuous recoil. And this can push anything away from the Earth and obviously eventually into space. So Newton's third law becomes quite critical when it comes to the ability to send rockets into space, and it's exactly what we have been doing for many, many years using Newton's third law. Now, all three of Newton's laws are necessary to understand orbital mechanics. We're missing one piece of the puzzle though, and that is the concept of gravity. And in the next video, we'll spend some time talking about the universal law of gravitation, and then we'll put that together with Newton's 3 laws, and we'll finally have everything we need to understand orbital mechanics. So we're almost there, a few more videos to go, but we'll get to the end. I hope you'll join me.